So maybe you were wondering, or maybe you were just hoping that we'd never get to this, but some of you might be thinking to yourselves, can you apply these principles that we've seen work in one-dimensional collisions, both elastic and inelastic? Can you apply that to two-dimensional collisions? And the answer is yes, of course you can, but it becomes quite a bit more complicated. So let's take a look at a kind of classic example of a two-dimensional collision. So let's say we have one mass, we'll call it M1, and it's got a mass of 1/4 of a kilogram, and it's traveling at 2 meters per second. And it's heading straight toward this other mass, M2, which is 0.4 kilograms, but it's at rest. Okay, so after this mass strikes the second mass, both masses are moving, and we know that the first mass is moving at 1.5 meters per second now rather than 2, so it's slowed down a little bit. And it's traveling at an angle 45 degrees north of its initial angle. So if it was traveling east, it's now traveling 45 degrees north of east. And from this information, we want to figure out what is the velocity of that second mass that was originally at rest, and what is the angle at which it's traveling. Now, if this first mass is traveling at an upward angle, then probably the second mass is traveling at a downward angle. We don't know that for sure, but whatever that angle is, it'll shake out in our calculations. So let's take a look at how we set it up. So with a one-dimensional collision, you can set up just a sort of generic conservation of momentum. So the initial momentum is going to equal the final momentum. In this case, we want to set it up for both the x direction and the y direction. Okay, so we'll look first at the momentum in the x direction. So if we're calling horizontal or eastward our positive x direction, the initial momentum in the x direction is just going to be the momentum of this object because this object's at rest. Okay, so we'll say that m1 times v1, that's going to be our initial momentum in the x direction. The question is, what do we set that equal to? So we want to set that equal to the x momentum of both of these objects. Okay, so for instance, the x momentum of this is going to be this mass times this velocity times the cosine of this angle here, because we only want to consider the x velocity. The x velocity is the only velocity that contributes to x momentum. Okay, so we're going to have m1 v1 prime times the cosine of 45 degrees. Okay, plus the x momentum of this second object. So that's going to be m2 times v2. We don't really need a prime mark for v2 because initially m2 is just at rest over here. So we'll do m2 v2, and again, this is going to be times the cosine of whatever angle it is. We don't know what it is, so we're just going to call it theta for now. Okay. We can also think about the momentum in the y direction. Now, this one is actually pretty nice because if we notice, if we're calling this the x direction, initially this object isn't moving in the y direction at all. Neither is this object because it's at rest. So, so our initial momentum in the y direction, I'll kind of label this here. So this is the x direction. And here we have in the y direction. Okay, so this 0 is going to be equal to the y momentum of our first object. So that's going to be m1 v1 prime times now the sine of 45 because we're looking in the y direction, plus m2 v2 sine of whatever that angle theta is. So there's a few different ways that we can approach this, but basically what we want to do is treat this almost like a system of equations. So we have a bunch of things that we do know. So we know m1, we know m2, we know v1, and we know v1 prime, we know this angle. We don't know v2 and we don't know this angle here. So we've got two equations and we've got two things that we don't know. So we want to basically just approach it like a standard system of equations. So probably the easiest way to do that is to take a look at this second equation that we have here, the equation for conservation of momentum in the y direction, and rearrange it a little bit. So maybe we can subtract this first term over here, and so we'll get m2 v2 sine theta equals minus m1 v1 prime sine 45. And we can really solve for whatever we want, but maybe we'll solve this equation for v2. So we'll do v2, and then we'll divide out this m2 and this sine theta. So we'll have minus m1 v1 prime sine 45 over m2 sine theta. So this equals v2. We can now take this expression for v2 and plug it back into our first equation, okay? So we'll have m1 v1 equals m1 v1 prime cosine 45 plus, now we're going to plug this whole thing in for v2. But notice we have m2 up here kind of in the numerator, and we're going to have m2 in the denominator. So the m2s are going to cancel out. That's kind of nice. And then we have cosine of theta divided by the sine of theta. So that's going to give us the cotangent of theta. So everything else kind of shakes out. So we have plus, now we can change this to a minus because we have that minus m1. So this is going to be minus m1 v1 prime sine 45 times the cotangent of theta. So now we've reduced it to a state where the only thing that we don't know is this this value here, cotangent of theta. But there is a way to kind of deal with that, work around that. So we can kind of plug in all of the known quantities here. So we'll do, let's see, we'll do m1 v1 minus m1 v1 prime cosine 45 plus m1 v1 prime, plus we're going to divide through by minus m1 v1 prime sine 45, and that's going to equal the cotangent of theta. So you probably don't have an arc cotangent button on your calculator, so all you have to do is just swap the numerator and denominator here, and you can say that the tangent of theta is equal to minus m1 v1 prime sine 45 over m1 v1 minus m1 v1 prime cosine 45. So we'll plug that into our calculator. Might take a little bit of time, but we know that m1 is 0.25 times v1 prime, that's 1.5, times the sine of 45, divided by, then we're going to have m1 times v1, so that's 0.25 times 2, minus m1, so that's 0.25 v1 prime, so that's 1.5 times, times the cosine of 45. And we get about negative 1.129. And so we just take the inverse tangent of that, and we get that theta is about negative 48.5 degrees, or we could say 48.5 degrees south of east. Okay, so it is traveling in the sort of direction that we predicted. So this is a 45-degree angle here. This is going to be like a 48.5-degree angle here, but it's going to be south of east instead of north of east. And from there, if we want to know what the velocity v2 of this second object is, we can really kind of take our pick, because now we only have one unknown in a sense. So we can kind of just plug things back into this equation here. So we do, let's say we'll do minus 0.25 times 1.5 times the sine of 45, and then we'll divide that by m2, which is 0.4 times the sine of theta, and theta is minus 48.5. We plug that in, and we get that V2 is about 0.886 meters per second. Okay, so that's just an example of how you would do a typical two-dimensional collision problem. Obviously you can rewatch this video as many times as you want if you're not following a certain step, or post any questions. And tomorrow morning I'll post an assignment related to two-dimensional collisions.